A rainbow snow cone is leaking from its paper cone at a rate of 2 cubic inches per minute. The paper cup's top radius is 3 inches and the paper cone is 5 inches tall. How fast is the radius of the snow cone changing when the radius of the snow cone is 2 inches? Okay, pause the video and try it, and then I'll give you my solution. All right, so when doing a related rates problem, the first thing I like to do is write down all my givens. So it says that the rainbow snow cone is leaking from its paper cone at a rate of 2 cubic inches per minute. So that means the cubic inches per minute is a clue that I'm dealing with volume. So that means my dV dt is going to equal, and since it's leaking out, we're losing volume, so it's going to be -2. The paper cone's top radius is 3 inches, so I'm going to use this little triangle here as the front view of the cone. So the top radius is 3. Okay, so let's put a middle point there. And the paper cone is 5 inches tall. So let's make a height here of 5 inches. So you can see that we have a right triangle here, and this is going to be important as we solve this problem here. So we want to figure out how fast is the radius of the snow cone changing. So how fast is the radius of the snow cone changing? Well, what rate is that? That is dr dt. So that's our unknown. When the radius of the snow cone is 2 inches. So we want this when r is equal to 2 inches. Okay, so now what formula ties this all together? Well, since we're dealing with volume of a cone, it's the volume formula for a cone, which is volume is equal to 1/3 pi r squared times h. All right, so the issue we have with this is we do not have a dH dt in our given. Okay, so that means what we're going to have to do is we're going to have to use similar triangles. Looking at the cutout of our cone here, the front view of the cone, we're going to do similar triangles, and we're going to solve for h in terms of r, so we can sub into the formula. All right, so this is an important problem when dealing with cones that you have to be able to handle here. So we're going to just assume that at any point within the cone, we have an r over h. So we have a triangle here. So we have the bigger right triangle with a radius of 3 and a height of 5, and a smaller right triangle at any level within the cone, which is r over h. So that means that 3 over r is equal to 5 over h. So that means we can solve for h here in terms of r. So we would get 3h is equal to 5r. So h is equal to 5r divided by 3. All right. So now what I'm going to do is I'm going to sub in 5r over 3 for h into my volume formula. So I get 1/3 pi r squared, and then h is 5r over 3. I'm going to simplify this. So it looks like I would get 5 pi r cubed. So I get 5 pi r cubed divided by 9. Okay. So now we're ready for our derivative that'll get our rates involved over here. Okay, so I'm going to work left to right. The derivative of v with respect to t is dv dt. The derivative of 5 pi r cubed over 9 would be 15 pi r squared over 9, and then it's implicit, so we would have a dr dt. Now in this case, at this point, I'm going to sub in my values. So dv dt is -2. My radius, we're solving for this one, the radius is 2, so we're going to put in 2 for the radius. All right, so let's simplify that. So we would get negative 2 is equal to, it looks like we have 4 times 15, so we'd have 60 pi over 9 dr dt. And then to solve for drt, we would multiply by the reciprocal of 60 pi over 9. So it looks like we would get negative 18 over 60 pi. And then the units would be inches per minute. And that would equal my dr dt. Okay? All right, so this would be an example of doing a related rates with the volume of a cone where you'll have to convert h in terms of r, and there are other problems where you want to find dh dt where you have to go the opposite way. So r in terms of h. So I hope that was helpful for you as you're working through related rates, and if you liked the video, please like and subscribe. Thanks for watching.